So next we'll look at some properties of transposes, and we'll state it as a lemma. So let A and B be M by N matrices with row entries. Let C be an N by P matrix with row entries. And let K be any real scalar. Then the transpose of the transpose of A is the matrix A. The transpose of a sum is the sum of the transposes. The transpose of a scalar multiple is the scalar multiple of the transpose. And the transpose of a product is the product of the transposes in reverse order. So proof. First statement. The entry in row I, column J, of the transpose of the matrix A is the entry in row J, column I, of the transpose of A, and this is the same as the entry in row I, column J, of the matrix A. And so the transpose of the transpose of A is the matrix A. So second statement. The entry in row I, column J, of the transpose of the sum A plus B is the entry in row J, column I, of the sum A plus B. This is the sum of the entries in row J, column I, of the matrix A, and row J, column I, of the matrix B. Now, the entry in row J, column I, of the matrix A is the same as the entry in row I, column J, of the transpose of A. And the entry in row J, column I, of the matrix B is the same as the entry in row I, column J, of the transpose of B. And so the transpose of a sum is the sum of the transposes. So third statement. The entry in row I, column J, of the transpose of the scalar multiple K times A is the entry in row J, column I, of the scalar multiple K times A. This is the scalar K times the entry in row J, column I, of the matrix A. And the entry in row J, column I, of the matrix A is the same as the entry in row I, column J, of the transpose of A. And so the transpose of a scalar multiple is the scalar multiple of the transpose. So fourth statement. The entry in row I, column J, of the transpose of the product B times C is the entry in row J, column I, of the product B times C. This is the sum of the products of the entries in row J, column K of the matrix B with the entries in row K, column I of the matrix C. Now the entry in row J, column K of the matrix B is the same as the entry in row K, column J of the transpose of B, and the entry in row K, column I of the matrix C is the same as the entry in row I, column K of the transpose of C. This is a product of real numbers, and so it commutes. So we have the product of the entries in row I, column K of the transpose of C with the entries in row K, column J of the transpose of B, and this is the entry in row I, column J of the product of the transpose of C times the transpose of B. And so the transpose of a product is the product of the transposes in reverse order. Now we can prove a stronger version of this statement, and we'll prove it as a theorem. So let A sub 1, A sub 2, and so on through A sub n be matrices such that the product A sub 1 times A sub 2 and so on through A sub m n is defined. Then the transpose of the product is the product of the transposes in reverse order. So proof. Let P of n be the statement that the transpose of the product of n matrices is the product of the transposes in reverse order. Then P of 1 is the statement that A sub 1 transpose is equal to A sub 1 transpose, which is true. So now suppose that the transpose of the product of the matrices A sub 1 through A sub k is the product of the transposes in reverse order, where k is greater than or equal to 2 and less than n. Then, by part 4 of the previous lemma, we have that the transpose of the product A sub 1 through A sub k times A sub k plus 1 is the product of the transpose of A sub k plus 1 with the transpose of the product A sub 1 through A sub k. Now since the product the transpose of the product a sub 1 through a sub k is the product of the transposes in reverse order. We have a sub k plus 1 transpose times a sub k transpose, and so on through a sub 1 transpose. And hence P of k implies P of k plus 1, and therefore, by the principle of mathematical induction, we have that the product, or correction, the transpose of the product of n matrices is the product of the transposes in reverse order for any positive integer n. So new definition: a square matrix A is symmetric if and only if the matrix A is equal to its transpose. Now recall that the Kronecker delta, delta sub ij, is defined to be 1 if the indices I and j are the same, and 0 if the indices I and j are not the same. So notice that the Kronecker delta, delta sub ij, is the same as the Kronecker delta, delta sub ji. And we can use this fact to show that an identity matrix is symmetric So proof: the entry in row I, column J of the transpose of an identity matrix I is the entry in row J, column I of the identity matrix. This entry is equal to the value of the Kronecker delta, delta sub Ji, which in turn is the same as the value for the Kronecker delta, delta sub ij, and this is the same as, this value is the same as the entry in row I, column J of the identity matrix. And so the identity matrix is equal to its transpose, and hence an identity matrix is symmetric. So next we'll prove another theorem. If the matrix A is an invertible matrix, then the transpose of A is also invertible, and in fact the inverse of the transpose of A is the transpose of the inverse of the matrix A. a proof. Again, by part 4 of the previous lemma, we have A transpose times A inverse transpose is the transpose of the product A inverse times A. This is the transpose of the identity, which is the identity. Similarly, the product A inverse transpose times A transpose is the transpose of the product A times A inverse, which is the transpose of the identity, which is the identity. And hence, A transpose is invertible. And its inverse is the transpose of A inverse. So let's look at an example. Let A be the 3 by 3 matrix with rows 1, 2, 3, 2, 5, 3, 1, 0, 8. Recall that the inverse of A is the 3 by 3 matrix with rows negative 40, 16, 9, 13, negative 5, negative 3, 5, negative 2, negative 1. So the matrix A is invertible. And so the transpose of A, which is the 3 by 3 matrix with columns 1, 2, 3, 2, 5, 3, 1, 0, 8, is also invertible. And the inverse of A transpose is the transpose of A inverse, which is the 3 by 3 matrix with columns negative 40, 16, 9, 13, negative 5, negative 3, 5, negative 2, negative 1.